Hello everyone, welcome to another video on chemistry, and we continue with organic reactions. Today I have two types of reactions we're going to focus on: elimination reactions and substitution reactions. So let's get right into it. Number one, in this case 1.2, we had 1.1 in the previous video where we were focusing on combustion. Now 1.2 is elimination reactions. And I'm going to describe a couple of elimination reactions. Number one, dehydrohalogenation. Number two, dehydration. Number three, dehydrogenation. And number four, cracking. And then I'm going to talk about substitution reactions, a special substitution reaction known as hydrolysis. I'm going to cover it together with dehydrohalogenation because they are very close in terms of the conditions. And then I'm going to give a simple general example on substitution reactions. So let's start with dehydrohalogenation. Now, let me say 1.2.1 dehydrohalogenation. Hydrohalogenation. Basically, removal of hydrogen and a halogen. So that means we are focusing on haloalkanes. Let's give an example here. And I'm using structural formula to describe these reactions. So let's consider this one here, which is 2-bromobutane. Reacting with concentrated strong base, for example, sodium hydroxide, in alcohol. And the other reaction condition is high temperature or extreme heat. Extreme heat or heat under reflux. Extreme heat or high temperature. So what happens here is the following. We have to decide whether one of the products or the organic product formed is a minor product or a major product. If the question requires that the product is a major product, then there's a rule that we need to apply. It's called Zaitsev rule, which implies that we are focusing or we want to produce a major product. This is applied for a major product. Major product. We're talking about the organic product. So what does it say? What does Zaitev's, or some people say Zitev's rule, what does it say? It says obviously the group 7 element, the halogen, will be removed. But when you look at this carbon and that carbon there, this carbon has 3 hydrogens. That carbon surrounding this carbon here, which contains the functional group, which is the halogen, these 2 carbons that surround this one has fewer number of hydrogen atoms compared to this one. This one has 3, that one has 2. And Zaitev's rule says it's this carbon, hydrogen here, that must go, and not this one, for a major product. So it means that if we're focusing on a major product, we're basically talking about these 2 guys going. So we are going to form a major product which says that there's got to be a double bond in the center there. So carbon, carbon, we have a double bond there, and then we have a carbon like so. This then is our major product. And don't forget that the two substances removed, the hydrogen and the bromine, must combine with the sodium hydroxide. So how does the combination happen? The sodium combines with the halogen and the hydrogen combines with the OH to form water molecule. So we now have two inorganic products besides this major organic product. So that's a major product, which is our organic product, which is actually but 2-ene. And then we have sodium bromide plus water, which is your H2O like this. This is an ionic substance, covariant substance. Okay, so that's our dehydrohalogenation. Take note of the conditions here. We have concentrated strong base. You can have potassium hydroxide or you can have lithium hydroxide. In this example, I have used sodium hydroxide. That's one condition, concentrated sodium hydroxide. In alcohol, why alcohol? Well, alcohol is a solvent for the haloalkane. So alcohol performs the function of dissolving this one here. And then we also need to have extreme heat. So two conditions there, concentrated sodium hydroxide and extreme heat or high temperature. The two conditions are needed for this elimination reaction. So that's the name of reaction. The type of reaction is elimination. The major product formed is this one, and then we have sodium bromide here, and then we have water. Now, notice something, that these conditions here must be remembered at all times, the two conditions here. However, if the question required us to obtain a minor product, then Zitep's rule would have been disobeyed. In other words, instead of having to remove that, we would have removed this hydrogen here, and so would have removed this hydrogen here, and so we would have had but1-ene. The double bond would have been on this in this place here. So let me put on the side here and say minor product somewhere here. So this produces, Zitep's rule produces a major product, but you can also have a minor product. That would be carbon, 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 double bond there, and your carbon, like so. And then you would have this. This then would be the minor product. If you were required to produce a minor product, this would be the one. This would be the one, minor product right there. It would be this one, but this is the major product. All right, so this is dehydrohalogenation. Now I want to describe a reaction that's very close to this one, but it's a substitution reaction. So you watch the conditions they have, what I'm going to say on the two conditions, what changes we're going to introduce there, and then you watch the reaction that becomes a substitution reaction, a special substitution reaction known as hydrolysis. So here we go. Similar to this one. So I'm going to say similar to the above reaction, is a substitution reaction known as hydrolysis. Now, how does it look? Well, here is how it looks. So we have again our haloalkane, 2-bromobutane, again reacting with a strong base, but in this case, instead of having a concentrated strong base, we have a dilute strong base. So check the change in condition there, dilute strong base. I'm going to use sodium hydroxide again, still in alcohol. Some books will say in ethanol, but we know ethanol is an alcohol. Now watch, the other change in the reaction condition. Instead of extreme heat here, if you check, instead of extreme heat there, I'm going to have mild heat. So dilute, mild heat, then the reaction changes from an elimination reaction to a substitution reaction. So watch. Mild heat, and what I'm going to produce is the following. The OH group is going to move from there to that place, and that one there is going to move to that place there. And what do we produce? We produce, obviously, two products. We have the alcohol now there, which is butane 2-ol in terms of IUPAC name. The OH has gone into that place, and the Br has come there, and so I'm going to have sodium, another product, sodium bromide. So I have two products now, whereas in elimination, I have three products. You can see here, in elimination, there are three products. We have the major product, all the minor product, depending on what the question requires you to do. And then we have sodium bromide, inorganic, water inorganic, organic, two inorganic products. Here we have organic product and one inorganic product. So this type of reaction is a substitution reaction. The name of the reaction is hydrolysis. So that's the name. Type of reaction. Type of reaction. It's actually substitution reaction. Please take note of this. This question is extremely highly examinable. Very, very highly examinable. Take note of the two. Now, I've given you the reaction conditions. If they ask you for reaction condition of hydrolysis, it will be dilute, strong base, and mild heat. Reaction for condition for elimination, dehydrohalogenation, it would be concentrated, strong base, and extreme heat or high temperature, right? So that is sorted, and a special substitution reaction called hydrolysis, it's covered. We have one more there from substitution reaction, general substitution reaction, which I'm going to describe. But let me move now to dehydration, which is basically removal of water. So it means we have an alcohol now. We're going to get rid of water. Dehydration. So again, Zaitev's rule will apply if they require us to determine the major product or minor product, depending on the alcohol. In this case, if I had, for example, if I had 2-bromopropane, I would be at liberty to remove either this one or that one. There would be no need for us to apply Zaitev's rule in terms of elimination here. Let me repeat that. If I had, with excluding this part here, if putting hydrogen there, if I had 2-bromopropane with these two conditions here, I would be at liberty to put a double bond this side or that side, and there would be no need for Zaitev's rule, because the two carbons surrounding this one would have the same number of hydrogen atoms. This one would have 1, 2, 3, and this one would have 1, 2, 3. So no need for application of Zaitev's rule there. Okay, but in this case, we had it because this carbon here had 3 hydrogens and that one had 1, 2. So we had to remove that one by Zaitev's rule, aiming at producing the major product. All right, now let's go to what I'm going to call 1.2.2, and this is dehydration, removal of water. Removal of water. Let's just give a simple example here. Suppose I had this one here. Again, I'm going to emphasize on Zaitev's rule so that at least that point is driven home. If this is what I had, and this is the OH group is on carbon number 2. and we have 1, 2, 3, 4 carbons in the main branch there, in the main chain. Then this would be butane 2O. Now again, by Zaitev's rule, if this is supposed to undergo elimination reaction, what are the conditions? Well, now in this case, I'm not reacting this with anything. I'm just going to make sure that I have strong, concentrated, strong acid, for example, sulfuric acid. Some people say sulfuric acid or phosphoric acid, concentrated strong acid. Applying Zaitev's rule to produce the major product, these two would go. So I would have 1, 2, 3, 4 double bond in the center there. And then if I'm interested in the minor product, the opposite would happen, as I've explained in the previous example there. This is what you would have. And then these two would form your water molecule, like so. There is your dehydration. The reaction condition, concentrated strong acid, remove of water. Again, if I had propan 2O, I would be at liberty to remove either this hydrogen or that hydrogen. So it doesn't matter where the double bond is placed, because there would be no need for application of Zaitev's rule. There is your elimination reaction by the name of dehydration, removal of water. I'm moving on to the third kind of elimination reaction, which is dehydrogenation, removal of hydrogen. 1.2.3, 1.2.3, dehydrogenation, removal of hydrogen. Let's give an example. So this one here, dehydrogenation, I'm basically focusing on, I have, let's say, an alkane. And this alkane would be, what if we have propane this time? And what do I need for this to undergo dehydrogenation? Well, I need a catalyst, for example, platinum or palladium, whatever catalyst would be required. These are the most famous ones. Platinum, palladium would be needed here, and many more, right? And then what happens is, again, when you look at these carbons here, they have the same number of hydrogen atoms. So obviously the center one will go and the other one will go. So what do I have? I have a product here now that says 1 carbon, 1 carbon, 1 carbon, and I have a double bond there. And then I have 2 hydrogens this side, and then this is the molecule I have. And obviously the 2 hydrogens will form a hydrogen molecule, like so. That is my dehydrogenation, removal of hydrogen from the alkane. So this is propane, and I'm producing propene. No need to indicate the position of the double bond there. Propene, and then I have hydrogen there. Right, let's look at 1.2.4. 1.2.4, which is cracking. Basically breaking down large alkane molecules into smaller alkene plus alkane molecules that are more useful. So let's give an example. The examination guidelines do have the definitions. If you are watching this video from South Africa, grade 12 examination guideline does have some of the definitions I'm focusing on here, but this one is very critical. They would require you to define it, so let me define it. It is the process. It is the process by which large alkane molecules are broken down to smaller let's say small alkane molecules, alkane plus alkene molecules that are more useful. Now there are 2 types of cracking. Remember, cracking is an elimination reaction. The name is cracking, but the type of reaction is elimination. There are two types of cracking. Type number one is called thermocracking. We use high temperature and obviously by Gay-Lussac's law, high pressure. So let's give an example. You would have C8H18. It's an alkane, so it's CnH2n plus 2. Remember, 2 times 8 is 16 plus 2, 18. We're breaking, this is octane by the way, we're breaking it down into an alkene. Let's say C2H4. This is ethene. To obtain ethane, I'm going to have to obtain an alkane, I'm going to have to subtract the subscript. So 8 minus 2, I'm talking about carbons now. 8 minus 2, it will be 6. And 18 minus 4, it will be 14. So this is ethene and this is hexane. An alkene plus an alkane that are more useful than this one. So that the condition here, because of thermocracking, I'm going to say high temperature here. Whenever you see high temperature, you know it's thermocracking. So if they've given me these two, I can work backwards by adding the subscript. So 2 plus 6 is 8. 14 plus 4 is 18. So it doesn't matter where you come from. They can hide this one, give you these two, you can work out that. They can hide this one, give you these two, you can work out that. Or this one hidden, you can work out that by using these two. So just take note of that. If this one is given in the form of a condensed molecular formula, what do you mean? Suppose you have this. You have 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. So this would be the case, just to give you an idea, because you'd never know what the examiner will be interested in. So filling these spaces here with hydrogen, and I'm using a straight chain one here, but we know we can have isomers of that one, but we will not talk about isomers in this lesson. Probably in the other lesson coming up, we'll deal with isomerism. Like so. There you go. Condensed molecular formula for this one is going to be CH3, this part here, this part, CH3, right? And the CH2s are 1, 2, 3, 4, 5, 6. So I'm going to have brackets there, CH2, and I have 6 of them, and then I have another CH3 at the end. That's the condensed molecular formula from octane, this one here, straight chain octane, or even if I have an isomer of octane, condensed molecular formula would look like that. Now, if this is what I've been given, and they're asking me to write down a balanced combustion, a balanced cracking reaction in which one of the products is ethene, I would have to come from here, draw this one, and then from here be able to work out that, and then do this equation here, but of course respecting the fact that they have given me that substance. So this format of octane would be in that position. So I would still be expected to have this one in that position and have these two. So for me to see these two, it will be easier for me to move from here to there. Okay. You would say maybe I don't need to go via that. It's up to you. You can still say, how many carbons do I have here? We have 1, 6, that's 7, 8 carbons. And how many hydrogens? That's 12 plus 6, that's 18. You can still do that and still be able to come up with these two, but they would expect you to have that in that place if this is what you've been given. All right, thermocracking. Let's move on to the next type of cracking, which is catalytic cracking, applying a catalyst. So type of cracking number 2, catalytic cracking, applying a catalyst. If I'm to use the same one, let me use decane this time, C10H22, and then I'm going to say, now I'm applying platinum, a famous catalyst that we use in catalytic cracking. And then let's say now I'm producing propene, C3H6, and then I would be required to work out the alkane. So this is an alkane. The alkane would again be obtained in the similar fashion. 10 minus 3 is 7. So I'll have C7 here, 22 minus 6, and that would be 16. So it will be H16. And yes, this one obeys the general molecular formula of alkanes because 2 times 7 is 14 plus 2, 16. So Cn, H2n. So this is catalytic cracking. How do I know? There will be a catalyst there. They can ask me, what type of cracking is this? Or they will say, what type of reaction is this? And name the reaction. So I would say, this is an elimination reaction. The name of the reaction is catalytic cracking or just cracking. I would still be awarded marks. Right, so the elimination reactions, we've described all of them. You have dehydrohalogenation. That was the first one to describe. Here it is. I've used one example here, but in an exam, maybe they will use a different substance there. And notice that these reactions here would be assessed in the form of a flow diagram where they put all the reactions in one. But if you know each one of them individually, even if they put them together, you'll still be able to understand what's going on and be able to answer questions that are posed at the end of your flow diagram. So dehydrohalogenation, the first elimination reaction we've spoken about. Someone would say dehydrobromination. That's also accepted as a name for this type of elimination reaction. Remember the major product there, application of Z-Tape's rule for the major product, and disobeying that produces the minor product over there. And then you have two inorganic products besides your either minor or main organic product. They would also be asking you, maybe in some cases, to provide IUPAC names of these substances. So in this lesson, I'm just going to mention them, but there are rules and laws that are required for you to be able to apply to name these organic substances correctly. So this is, for example, this would be but1-in, this would be but2-in. This one obviously is sodium bromide, and that's your water. And that's your 2-bromobutane. It's a haloalkane. That's an alkene, that's an alkene, that's an inorganic substance, obviously. An ionic, metal, non-metal, ionic, there's complete transfer of electrons there. And that's why we don't indicate the bond in between the two. And then you have water over there, right? So this is an elimination reaction. The other elimination reaction we've spoken about is your dehydration, removal of water. Dehydration, removal of water. Do I have it here? Yes, here it is. Dehydration over here. 1.2, removal of water. I've given you an example there. Again, applying Z-Tape's rule for the major product. If we disobey that, we would obtain a double bond over here. That would be a minor product. And of course, we have water there as an inorganic substance produced. But then again, I said to you, if you remember, I said this reaction here is very close to and similar to a substitution reaction known as hydrolysis. If you check here, hydrolysis, the conditions, the only difference is that here, instead of using a strong, instead of using a concentrated strong base, we use a dilute strong base. Instead of using extreme heat here, we use mild heat, and then you would have differences in terms of products. We have two products here, an alcohol, which is in this case butan 2-ol, and then you have sodium bromide here, which you would also produce in the case of this dehydrohalogenation, which is an elimination reaction. Right, and then I moved on to talk about dehydrogenation, which is removal of hydrogen. Over here, there is an example, dehydrogenation, removal of hydrogen, and we said we need a catalyst there, palladium or platinum, and then you produce this substance. And cracking was the last example of elimination reaction. We've spoken about cracking as the process by which large alkane molecules are broken down into small alkane plus alkene molecules that are more useful. Two types of cracking. We have thermal cracking. I've given an example there where we use extreme heat, or sometimes they'll say high temperature, or they'll say high pressure. Pressure is directly proportional to temperature by Guy-Lussac's law. So instead of saying high temperature, they say high pressure. No, it's thermal cracking. Otherwise, catalytic cracking would require the use of a catalyst, and the famous catalyst that we use is platinum. And here's an example of catalytic cracking. There it is. That now, the last example that I want to give is, I promised you that I was going to give one general example of substitution reaction here. So just so that we just complete these two reactions. Substitution reactions. I'm just going to give one here because I've already given one major one. One would be, for example, you have methane reacting with, let's say, chlorine gas. What do we produce? Well, one chlorine atom comes here and hydrogen comes here. So we are going to produce CH3Cl plus HCl. In terms of structure, this would be this here, plus Cl, and then you'd have this hydrogen coming there and that chlorine going there. And so what do you produce? You produce C with hydrogen there, hydrogen, and in that place you have chlorine, but then you have hydrogen in that place, so HCl. So this is monochloromethane, and monochloromethane would also be involved in another substitution reaction. If we are to continue with this, this would go into another substitution reaction, like so, plus another chlorine molecule here, and then this one would go there, and that one would come in that place. And what do we have? We have carbon with hydrogen over here, like this, chlorine there, plus hydrogen chloride with hydrogen there. This would go into another substitution until all these are removed. So this is dichloromethane, and then you have trichloromethane, and then you have tetrachloromethane. So with trichloromethane, that's the one that if one is injured in hospital, or they want to remove your tooth, if you're having toothache, they would inject you with trichloromethane. It's used as anesthetic in hospital. Now, and then so these would continue until all the hydrogens are removed and replaced with chlorine atoms in there, and then you form what is known as tetrachloromethane finally. All right, if you're new to this channel, please subscribe, share these videos. It will help us to grow this channel and give us the impetus to bring more videos of this nature. We hope this will make a difference. In my next video, I'm going to be talking about the remaining types of reactions. Remember, now we have spoken about combustion, we've spoken about elimination, we've spoken about substitution. We're left with three types of reactions, and these are esterification, and then we have addition reactions. We're left with two actually, because cracking is usually taken as a type of reaction on its own, but we know that it's under elimination. So out of 5 reactions, main types of reactions, which are combustion, elimination, addition, esterification, and substitution, we have discussed so far combustion, elimination, and substitution. We're left with esterification and addition reactions. So in the next video, I hope to deal with the 2 types of reactions. See you in the next video. Thank you.